Cute type, ugly type, cute type, ugly type, cute type, ugly type, cute type, ugly type. Funny type, not so funny type, funny type, not so funny type, funny type, not so funny type. Cute type, funny type. No. Funny type, cute type? No. Cute and funny? Yes, yes. Ugly and not so funny? Yeah. You want to learn some game theory, bud? You ready for some game theory? Because now that I'm done with my shameless ISIS form inflation attempt, let's get started! Hey everybody, welcome to PS 231. Oh, this is going to be a doozy. This is going to be a doozy. That's why I didn't even put any time into thinking about the cold intro. I don't have time to think about the cold intro because I am about to deliver some messages from my head to your head. You have no idea what's about to hit you, but it's something. Actually, I don't either, but it's something. So in the previous lecture, we talked about how to incorporate information into our Book of Fables. Our Book of Fables is now getting pretty thick and all sorts of cool stories are in there. And I think that you'll agree with me that some of the coolest stories we've talked about so far have emerged since last week. Like in the last 7 days, we've come up with some cool stuff. Well, we haven't. Some other smart people have, and my job is to convey it to you. But there's all sorts of cool stuff that involves private information. What happens if you know something that somebody else doesn't? Even if we are both rational sociopaths, that doesn't mean that we have the same data available to us, and therefore we may not come to the same judgments of things. And it turns out that the fact that different data can lead the same sort of player to different judgments is something that can really throw off all sorts of political processes. Or maybe not even throw off, maybe just characterize. And so what I want to do today is take those fables that we talked about last time, and I'm going to show you how to get to the ending of these more complicated stories. Oh man, in order to do so, I'm gonna have to get my armrest exactly where I want. Oh, look at that. Oh, that's perfect. Oh, that's perfect. You have no idea what's about to hit you. You're gonna be stupefied all day. So the ending of these incomplete information fables, oftentimes, you don't get to one like firm ending. Games like this, the number of equilibria tends to explode pretty fast. But you'll see that there's a nice way for us to think about the equilibria in a substantive sense. I know it's hard to believe. I know with all of the computation and all the technical mumbo jumbo and all the furrowed brows and all the late nights of your problem set and all the questions that you asked a meeting and that I tried to answer and I didn't do a very good job of, I know that despite all of that technical stuff, I know that despite the fact that this feels like a math class, it's not. It's not a math class. I'm not a mathematician. I don't know about math. But what I do know is how to teach you how to tell stories this particularly weird way. And so as we get closer and closer and closer to the top of the mountain that I'm trying to get us to the top of within 15 weeks, I hope that you're paying more and more attention, not to the technical machinery, not to all of this apparatus, not to all of the numbers and the loops and the colors and the shapes and the, oh my goodness gracious, what do I throw at you? I throw too much at you. I hope that you're finally getting ready to see this for its substantive punchlines. There have been some really important punchlines along the way: completeness and transitivity, von Neumann and Morgenstern, bargaining and optimality. What is equilibrium? What is best response? What is credibility? How does time throw off equilibrium? I mean, there's all sorts of interesting things that have popped up along the way, but I think these last few weeks have the best chance of like, boom, hitting you hard so that you resonate and you see that what this is just a language for talking politics. So because we're getting so close to the top of our mountain, because we're coming so close to the end of our time together, let me not waste any more time. Just get yourself strapped in. Just get yourself ready. Let's push up this mountain. Let's get to it. In the A block, we'll finish up the story of the musical companions. That's it. In the B block, we'll talk about the swing voters curse. And in the C block, we'll talk about pivotal politics. If that doesn't whet your appetite, then you haven't been thinking hard enough the past few weeks. This is just the tip of the iceberg, and it's time to go a little bit deeper into the waters to show you just how big of an iceberg we're talking about. I have a lot of faith that if you just keep things slow, keep things simple, go step by step, And maybe you don't get everything the first time, but give yourself a couple of iterations. But if you give yourself the time and give yourself the space to screw up a little bit, because this is tricky, but if you give yourself the time and the space, I think you're about to learn something really cool. So let's get started. Feeling locked in? You feeling good? You feel inspired? I know that you got this, but if you don't know that you got this, then you don't got this. But I know that if you feel like you got this, hell, if I know that if you know that you got this, which you ought to know by now, but if you know that you got this, then you got this. And what do I mean by this? I mean the sad tale of the musical companion. So remember the basic idea of the sad tale of the musical companions, which might not be so sad, we'll see about that, but remember the basic idea is I'm a musical companion. You're a musical companion. We are two musical companions. Maybe. I'm a musical companion, proud and true, no matter what, ride or die. I'm a musical companion, proud and true. But what I don't know is whether you are also a musical companion, proud and true. You may be a musical nemesis, shameful and lying. What do I mean by that? I mean, there's two types of you, player two. There's two types of you, one of whom wants to hang out with me. There's no accounting for taste. One of you wants to meet at a show. One of you wants to play a coordination game with me. One of you is playing a coordination game with me. And one of you is playing an anti-coordination game with me. They might as well be pitchers and hitters, right? So one version of you wants to coordinate, and one version of you wants to anti-coordinate. Every version of me, which is all one kind of me, wants to coordinate. I'm a musical companion, proud and true. If you want me to tell you that I am not both proud and ashamed of all of the shtick in this, well, then I'm not going to tell you that because I'd have to lie. In order to encode this basic idea, I'm going to say that there's two kinds of you, and I'm going to draw them on different sides of my screen. One version of you is indeed a musical companion, proud and true. Look at that 24 frames a second. Look at that blurry hand. Seriously, that blurry hand is so delightfully blurry. This is so cinematic. Call Steven Spielberg. And the other version of you is a musical nemesis, shameful and lying, and doesn't want to hang out. Right? So here's one version of you, and here's the other. Oh, look at that. Oh my goodness. You have no idea how much core work it takes to do that. So here's the two versions of you. In order to show that you know which version you are, in the orange color that represents player 2 in our stupid apocrypha, I will draw two separate information sets. You know which world you're in, and thus we're. You know what kind you are. You know if you're a musical companion, proud and true. You know if you're a musical nemesis, shameful and lying. You get to know that because that's in your head. That's the sort of thing that lives underneath that monologue. You know, like when you go to a wedding. Oh, by the way, so the next 10 years, every summer is going to be full of self-righteous loathing. I just want to warn you, because all your friends are going to start getting hitched, which is fine. But as you see the same strangers again and again and again, and they don't become more than strangers, they're just people that you've seen before, they're not going to know if you want to hang out with them or if you want to hide from them. They don't know if you're like, oh, let's meet on the dance floor, or you're on the dance floor, oh, I'm going to go hit the carving station. Of course, you can guess that I play the carving station in Pure Strategies. But this is something in your head. This is something in your head. You know if you want to hang out with me or not. So inside each of these states of the world, we will put a game that looks like Bach or Stravinsky. In the state of the world where you're a musical companion, we will in fact draw Bach or Stravinsky, by which I mean I'm a musical companion, you're a musical companion, we are two musical companions. I can go to Bach or I can go to Stravinsky, you can go to Bach or you can go to Stravinsky. We have fables, we can just talk about the fables. If we both go to Bach, 2 happiness points for me, I love Bach, 1 happiness point for you, you're a musical companion. If we both go to Stravinsky, 1 happiness point for me, I'm a musical companion, 2 happiness points for you, you love Stravinsky. If we go to the different shows, we're crestfallen because we're musical companions and musical companions are ride or die, 0 happiness points apiece. Yeah, you signed up for this. You could have dropped. However, in the world where you are not a musical companion, proud and true, but rather are a musical nemesis, shameful and lying, in that world, I'm a musical nemesis, you're a musical nemesis, we are 2 musical nemeses. I can go to Bach or Stravinsky, and you can go to Bach or Stravinsky. I want to hang out with you. My favorite is Bach. I get 2 happiness points at Bach, but you're really pissed off because we're at the same place, so you get 0 happiness points there. My second favorite is Stravinsky, because at least we're hanging out together. I get 1 happiness point in Stravinsky, but you get 0 because you're stuck with me. At Bach Stravinsky, I'm crestfallen because even though I'm nerding out to all of the wonderfulness of Johann Sebastian Bach, I'm not with my musical companion, which is exactly what you were looking for. Now you're watching your favorite composer, Igor Stravinsky, without my ass next to you. 2 happiness points for you. And at Stravinsky Bach, I'm just as crestfallen as I was before, and you're happy but not as happy because in order to avoid me, you had to put up with Baroque music. 1 happiness point for you. This is the game of Bach or Stravinsky when applied to incomplete information with a weird narrative of the musical companions. Don't even act like you don't love it. And you'll remember that what makes player 1 uninformed is the fact that they have this one giant information set, which means that they make one and only one choice. They either go to Bach and they don't know which world they're in, or they go to Stravinsky and they don't know which world they're in. And remember, the other thing that makes me uninformed is the fact that I have only probabilistic expectations about which world we're living in. And just to keep things spicy and to have a unified approach across all 3 blocks, let's say that I think you're a musical companion proud and true with probability alpha. Alpha is a number that lives strictly between 0 and 1. It's the probability that I assign to you being a musical companion proud and true. It might be a half, maybe I just tossed a coin and guess. Maybe I think there's a 90% chance you're a musical companion proud and true. Regardless, alpha tells me how often I think we're living in this world, and 1 minus alpha tells me how often I think we're living in this world. Okay? Alpha, 1 minus alpha. That's going to be throughout. It's always going to be alpha for one type and 1 minus alpha for the other. Whereas you, player 2, you know what's happening in these 2 worlds. You can choose 2 different strategies. You can go to Bach in this world and Bach in this world. You can go to Bach in this world and Stravinsky in this world. You can go to Stravinsky in this world and Bach in this world. Boy, this is aim that is way too advanced for me. Or you can go to Stravinsky in both worlds. Right? So you have 4 different pure strategies. You have 4 different pure strategies because we need to know what you're going to do at both information sets. I need to know what you're going to do in the world where you're a companion proud and true, and I need to know what you're going to do when you're a nemesis shameful and lying. I need to know what you're going to do in both of those worlds. You might choose the same composer, but they're 2 separate choices, whereas I make one and only one choice. So given that you can do different things at different information sets, and given that I have only probabilistic expectations about which world we're living in, we need to think about what my expected utility of Bach is and my expected utility of Stravinsky is in response to each of your 4 possible pure strategies. I'm going to make a special kind of table that's got 2 rows, 1 for every choice that I have, and 4 columns, 1 for every choice that you have, where a choice for you means what you would do in the musical companion world and what you would do in the musical nemesis world. So in this new weird table that we're going to construct, I can either go to Bach or I can go to Stravinsky. But you can either play Bach Bach, Bach Stravinsky, Stravinsky Bach, or Stravinsky Stravinsky, where the first one is what you do in the companion world and the second one is what you do in the nemesis world. What I'm going to do is for each of the different possible outcomes here, I'm going to draw it so that you can see what the cells that we're taking averages across look like. So let me just start with a simple, straightforward question. What is my expected utility of playing Bach if you're playing Bach when a companion and Bach when a nemesis? Well, let's think about that. With probability alpha, you are the companion. And you are playing Bach when the companion, and so we're at Bach Bach, and I get 2 happiness points. So with probability alpha, I get 2 happiness points for being a Bach Bach with the companion. And with probability 1 minus alpha, you are the nemesis. And the nemesis is playing Bach. And so if you're the nemesis, we go to Bach Bach, and I get 2 happiness points. And so my expected utility for playing Bach against Bach Bach is 2 times alpha plus 2 times 1 minus alpha, which is just 2. Right? We don't need to bring information into this. If you're playing Bach either way, if I play Bach, I get the 2 that I get for Bach Bach. Similarly, if you're playing Bach Bach and I play Stravinsky, well, with probability alpha, you're the companion. We're at Stravinsky Bach and I get 0 happiness points. And with probability 1 minus alpha, you are the nemesis who is playing Bach. We're at Stravinsky Bach and I get 0 happiness points. So my expected utility for playing Stravinsky against Bach Bach is 0. We don't need to bring alphas into this. Just to drive that point home, let's go over to the Stravinsky column. What's my expected utility of playing Bach when you're playing Stravinsky? Well, with probability alpha, you are the companion who is playing Stravinsky, and I am playing Bach. We are at Bach Stravinsky, and I get 0 happiness points. And with probability 1 minus alpha, you are the nemesis who is playing Stravinsky in this world that we're thinking about. And if that's the case, then we're at Bach Stravinsky, and I get 0 happiness points. 0 times alpha plus 0 times 1 minus alpha, that's just 0 again. And my expected utility for playing Stravinsky when both types of you are playing Stravinsky. Well, with probability alpha, you're the companion who is playing Stravinsky. And we're at Stravinsky, and I get 1 happiness point. And with probability 1 minus alpha, you're the nemesis who is playing Stravinsky. And we're at Stravinsky, and I get 1 happiness point. So my expected utility for playing Stravinsky, when I think both types of you are playing Stravinsky, is alpha times 1 plus 1 minus alpha times 1 is 1, which is what I get for Stravinsky. Okay, so now let's suppose that you are playing Bach when a companion and Stravinsky when a nemesis. That sounds reasonable. So my expected utility for playing Bach against Bach when companion, Stravinsky when nemesis is, well, with probability alpha, you are the companion who is playing Bach. And we're at Bach, and I get 2 happiness points. So 2 times alpha. And with probability 1 minus alpha, you are the nemesis who is playing Stravinsky, and we're at Bach Stravinsky, and I get 0 happiness points. So it's just 2 times alpha. Now the alphas matter because the different types of you are doing different things. Suddenly that makes sense, right? Well, sense is a strong word, but you know what I mean. What about my expected utility for playing Stravinsky when you're playing Bach when a companion and Stravinsky when an avoider? Well, if you're doing that, I play Stravinsky with probability alpha. You're the companion who is playing Bach, and I get 0 happiness points. So 0 times alpha. And with probability 1 minus alpha, you're the nemesis. And the nemesis is playing Stravinsky in this world. So we're at Stravinsky, and I get 1 happiness point. So my expected utility for playing Stravinsky against Bach for a companion and Stravinsky for an avoider is 1 minus alpha. Finally, let's think about the world where you're playing Stravinsky when a companion and Bach when a nemesis. So if you're playing Stravinsky when a companion and Bach is a nemesis, and I play Bach. So with probability alpha, you are the companion who is playing Stravinsky, and I'm at Bach, 0 happiness points because we're at Bach Stravinsky. And with probability 1 minus alpha, you're the nemesis, and the nemesis is playing Bach, and so we're at Bach, and I get 2 happiness points, so it's 2 times 1 minus alpha, 2 minus 2 alpha. And finally, if I play Stravinsky, if you play Stravinsky when a companion and Bach when a nemesis, well, with probability alpha, you are the companion who is playing Stravinsky, we're at Stravinsky, 1 happiness point, alpha times 1. And with probability 1 minus alpha, you are the nemesis who is playing Bach, and I'm playing Stravinsky, 0 happiness points, so that's just alpha. So now we can work out what my best response is to each of your possible strategies. So for example, if I think that both types of you are playing Bach, then I can either play Bach and get 2, or I can play Stravinsky and get 0. I'll play Bach, I'll put a star next to that 2. And similarly, if you're playing Stravinsky, I can play Bach and get 0, or Stravinsky and get 1. I'd rather play Stravinsky, I'd take that 1, so I'll put a star next to the 1. Now there's some nuance. So you'll notice that Bach is a best response to Bach Stravinsky. So if my expected utility of Bach is 2 alpha and my expected utility of Stravinsky is 1 minus alpha, then Bach is better when 2 alpha is greater than or equal to 1 minus alpha, which works out to alpha greater than or equal to 1/3. So if alpha is greater than or equal to 1/3, I play Bach. I'd rather play Bach. And if alpha is less than or equal to 1/3, I'd rather play Stravinsky. If that's the situation. Similarly, if we're in the world where you play Stravinsky when a companion and Bach when a nemesis, well, 2 minus 2 alpha versus alpha, if you work all that out, Bach is better when alpha is less than or equal to 2/3. And if alpha is greater than or equal to 2/3, then you play Stravinsky. So what I want to do is I want to talk about 3 versions of the game, and in each of them, we will think through what you, the informed player, will want to do in response to what I'm doing. Suppose that alpha equals 1/6. If alpha equals 1/6, then my best response to Bach Stravinsky is Stravinsky, and my best response to Stravinsky Bach is Bach. Okay, because that's less than 2/3, and it's also less than 1/3. That's why I chose it. Let's think about whether you are happy. Does either type of you want to deviate? Now, what makes you informed is maybe one type of you would like to deviate. Well, let's think about this. So let's think about the companion. Right now, the companion, if you're playing Bach and I'm playing Bach, the companion is happy because if they deviated, we would go to Bach Stravinsky and they would go from 1 to 0. They don't want that. They don't want to deviate. The companion is happy. But the nemesis is like, wait a second, right now I'm stuck at this show getting 0 happiness points, and if I deviated, I could go to Bach Stravinsky and get 2 happiness points. They'd rather deviate. So it's not an equilibrium for me to play Bach when both of you are playing Bach. Now I'm talking about you like there's 2 of you, but you know what I mean, the meter and the avoider, the companion and the nemesis. It's not an equilibrium for me to play Bach when both of you are playing Bach. Because the nemesis is like, wait a second, I can deviate. Similarly, if I play Stravinsky and you're both playing Stravinsky, then the companion is happy. They wouldn't want to deviate because they would go from 1 to 0. But the nemesis is unhappy because they could deviate. If they deviated, they would go from Stravinsky to Stravinsky Bach and get 1 happiness point. So they don't want. There's not an equilibrium there. There will never be an equilibrium where both types of you play the same thing, because the avoider, the nemesis, is really unhappy about that. If you're playing Bach Stravinsky, my best response is Stravinsky because alpha's really low. So let's think about whether either of you wants to deviate. So I'm playing Stravinsky and you're playing Bach when a companion, and Stravinsky when a nemesis. Well, right now the companion is thinking, well, right now we're at Bach Stravinsky and they're getting 0 happiness points. They could deviate. If they deviated, we'd be at Stravinsky and they'd get a happiness point. So no, there's not an equilibrium like that, because at least one type of you would like to deviate. No type wants to deviate. That's what we're looking for. Now it's not just no player, no type of any player. No type of any player wants to deviate. Finally, if you're playing Stravinsky Bach, my best response is Bach. And again, the companion is thinking, wait a second here, I could deviate. Because right now the companion is going to a different show. The companion would deviate if they could. Nope. In this game, if alpha's really low, which is to say if we're really close to the nemesis world, which doesn't have an equilibrium, you'll notice, doesn't have a pure strategy equilibrium, then there's no pure strategy equilibrium. The only equilibria are in mixed strategies, and I will skip them because that's a nightmare. So if alpha's really low, which means that I think it's really likely that we're in the world of nemesis. If I think nemesis are really likely, then we're not going to be able to find an equilibrium, because there isn't a pure strategy equilibrium in the nemesis game. Now suppose alpha equals 1/2. Suppose I think it's equally likely that you're a companion or a nemesis. The only change is now that because alpha is greater than or equal to 1/3, now my best response to Bach Stravinsky is Bach. My best response to Bach Stravinsky is now Bach. I'm not going to check the other 3 because we already showed that those aren't equilibria. What I need to check now is it the case that when I play Bach and you play Bach Stravinsky, we know that I'm best responding, but are both types of you best responding? Well, right now the companion is at Bach and is getting a happiness point, and if they deviated, they go to Bach Stravinsky and get 0. They don't want to deviate. And the nemesis version of you, well, right now they're at Bach Stravinsky getting 2 happiness points, nerding out on the polyrhythm. If they deviated, they'd be at Bach and they'd be stuck with my ass. Nope. They don't want to deviate either. So in other words, if alpha is a half, if alpha is between 1/3 and 2/3, this game has one pure strategy, Bayesian Nash Equilibrium, where I go to Bach. If you want to see me, you go to Bach. And if you don't want to see me, you go to Stravinsky. Notice that only works if I think it's sufficiently likely that you're a companion. If I don't think you're a companion, then I don't go to Bach. Finally, suppose that alpha equals 5/6. So now it's bigger than 2/3 as well. So if that's the case, then my best response to Bach Stravinsky is still Bach. And so there's still an equilibrium there. But you'll notice now that my best response to Stravinsky Bach is now Stravinsky. I've switched. If I think that you're super likely to be a musical companion, then my best response to Stravinsky Bach is Stravinsky. You'll notice again that this renders the companion happy because we're at Stravinsky together, and it renders the nemesis happy because they're at Bach by themselves, which is better than Stravinsky with me, which means that there's a second Bayesian Nash equilibrium if it seems sufficiently likely that you are a companion. So whether or not there's 0, 1, or 2 predictions to think about depends on how likely I think it is that you're a companion or a nemesis. That drives this result. If I think you're likely to be a nemesis, then what happens is I try to go to Stravinsky when you go to Stravinsky because I'm a companion. And you're like, no, that won't work. And I try to go to Bach when you're going to Bach, and you're like, no, that won't work. And that's both the companion version of you and the nemesis version of you. Similarly, when I think it's very likely that you're a companion, if alpha is really high, if it's higher than 2/3, then I can just sort of say, well, if I think you're playing Bach Stravinsky, I'll play Bach. The companion version of you is happy, and the nemesis version of you is happy. And I can even do the same for Stravinsky, even though I don't like Stravinsky as much. So that the reason that the alpha has to kind of be high, small, medium, or large has to do both with what I think you're doing, but also what I want. I would like to meet at Bach if I can, right? A lot of this gets more nuanced because of the fact that I have heterogeneous preferences over the bargained outcomes, over the coordinated outcomes. But regardless, the power of alpha is all around us, right? Because of this, we're able to say, well, if I think you're a nemesis, there's not going to be a clean prediction. If I think it's intermediate, there's one and only one prediction. And if I think it's really likely that you're a companion, then I can find two predictions. All of this based on my prior belief about what kind of you are. It's pretty heavy when you think about it, right? I got some even heavier stuff to show you. So over in the B block, it's time to figure out what's going on underneath the swing voters curse. See you there. So here in the B block, I want to resolve the tension from your problem set by talking about the swing voters. All right, so this is the first time we've done it in a movie. Let me just show you the idea here. So the idea is that there's two voters. I'm a voter, you're a voter, we are two voters. And I'm the row voter and you're the column voter. But unlike other versions of voting models we've talked about, here we're going to allow the possibility for abstaining. And the basic idea here is that I don't know what's best for society. And you do. You're enlightened and I'm not. That's not that hard to believe. So suppose that you know what's best for society in terms of which candidate should win, and I don't. But we both have the possibility of voting or abstaining. So in other words, there's going to be two states of the world again. In this state of the world, candidate A is what is the person that we want to elect for society. Okay, so the basic idea here is that you get to know who the right candidate is. You know what's best. Congratulations. And in this world, candidate B is what's best for society. Okay? So here A is best and here B is best. And let me just zoom in on the world where A is best. So in this world, I'm the row voter and you're the column voter. I can either vote for A, or I can abstain, or I can vote for B. And you can vote for A, abstain, or vote for B. So in this state of the world, A is the correct candidate and B is the incorrect candidate. So if we both vote for A, 1 happiness point apiece. If you vote for A and I abstain, 1 happiness point apiece because A won. If I vote for A and you abstain, 1 happiness point apiece because A won. If we both abstain or if we vote for different candidates, a half a happiness point apiece for the tie. We got the right candidate half of the time. And if B winds up winning in the state of the world where we wouldn't want them to, 0 happiness points apiece. So in this state of the world, we have the same preferences. You'll notice there's no cost of voting. We just want to vote for the candidate that we think is best for society, which is something that you happen to know and I don't. So let's go over to the situation where candidate B is what's best for society. Again, I can vote for A, I can abstain, or I can vote for B. And you can vote for A, abstain, or vote for B. If B wins, 1 happiness point apiece. If A wins, 0 happiness points apiece. And if there's a tie, a half a happiness point apiece. So let me just zoom back out. So here's our situation. In the world where we want A to win, or where A is best for society, it looks like this. And in the world where B is best for society, it looks like this. You get to know what the state of the world is. You know for sure where we are, so I'll draw 2 separate information sets. You'll get to condition your choices on what you know. And I don't know, so I'm going to draw 1 gigantic information set that says I don't know. I make 1 and only 1 choice. Now, I again have probabilistic expectations over which state of the world we're in, and so we'll say that I think that A is the better candidate alpha of the time, alpha percent, with probability alpha, somewhere between 0 and 1, and I think that B is the right candidate with probability 1 minus alpha. So let me do this a little bit in reverse to speed up the analysis, because otherwise we're going to be going through a huge matrix. I don't want to have to work that hard. Let's zoom in on the world where A is the preferred candidate. Your best response to my voting for A is to either vote for A, which gets you 1, or to abstain, which also gets you 1. You can do either. Your best response to me abstaining is to make A win by voting for A. And your best response to my voting B is to make A tie for voting for A. So when you know that A is the better candidate, your best response to my voting for A is either to also vote for A or to abstain. Your best response to my abstaining is to vote for A, and your best response to my voting for B is to vote for A. And it's going to be the same situation in reverse over in the world where B is the candidate that's best for society. If I vote for A, you'd rather vote for B to force a tie. If I abstain, you'd rather vote for B to make sure they win. And if I vote for B, you could either abstain or vote for B and get 1 happiness point. Notice that your best response to my abstaining, the only possible best response for you, because there's no combinations of stars, the only possible best response for you when I am abstaining is to vote for A in the state of the world where A is what's best for society, and to vote for B in the state of the world where B is what's best for society. The only time that you have stars in the abstain row is when you vote for A if it's A, and when you vote for B if it's B. However, if I'm voting for A, then you can either vote for A when it's A and vote for B when it's B, or you can abstain when it's A, or you can vote for B when it's B, right? So there's 2 possible best responses for you if I'm voting for A. It could be that you vote for A and then vote for B, or it could be that you abstain and then vote for B. Either of those works just fine. Similarly, if I'm voting for B, then you have 2 possible best responses. It's either vote for A if it's A and abstain when it's B, or vote for A when it's A and vote for B when it's B. So there's 3 possible choices that you could make that are potential best responses for you, right? There's the one where you vote for A and then vote for B, the intuitive one. There's the one where you abstain and then vote for B. And there's the one where you vote for A and then abstain. Those are the 3 possible things that you could do that don't involve playing a strategy that's always worse than something else. Notice that we've ruled out the possibility of both types of you abstaining. So one of you is going to vote. It could be both of you vote. And again, whenever you vote for the person that is best for the state of the world. Notice that at least one type of player 2 votes, and anytime that a type of player 2 votes, they vote for the person that's best for the state of the world. Nothing perverse is happening in terms of the informed voter. Now let's think through my expected utilities of playing A, abstaining, and B in light of those 3 strategies that have survived the initial analysis on your part. So let's start from the intuitive world where if you know that A is best, you vote for A, and if you know that B is best, you vote for B. So if I vote for A, then with probability alpha, we both voted for A, and A was the right person, and I get 1 happiness point. And with probability 1 minus A, I just made a tie that I don't want. We're at AB, and I get a half a happiness point. That works out to 1 plus alpha over 2. If I abstain when you're voting A and then voting B, if I abstain when you're voting for who you know is best, then with probability alpha, I stayed out, you voted for the right candidate, 1 happiness point. With probability 1 minus alpha, I stayed out, you voted for the right candidate, 1 happiness point. My expected utility for abstaining, when I know that you're voting for the right candidate either way, is 1. And for voting for B when you're voting for the right candidate, well, with probability alpha, we are at the A state of the world. You're voting for A. I just made a tie. So alpha times 1/2 plus 1 minus alpha. Well, I kept B winning. So 1 happiness point. That works out to 1 minus alpha over 2. You'll notice that my best response when you're playing AB is to stay out. And you're perfectly happy about that because you get 1 happiness point in both states of the world. So we have found a Bayesian Nash equilibrium wherein I don't vote. If you know that it's A, you vote for A. And if you know that it's B, you vote for B. That's a good outcome, but it might not be a good normative thing, right? So typically people tend to think that more voters good. And here, in order to get the outcome that was best for society, the uninformed voter stayed home. right? I mean, it's intuitive. That one makes sense. Don't get in the way. And it has nothing to do with alpha, right? It had nothing to do with alpha because no matter what, you can just get the one happiness point, which has nothing to do with alpha. All the alphas do in the other two cells is take it further or closer to one, but it's never as high as one. The best thing for me to do, if I know that you're doing the right thing in either situation, is just to stay out and let you do that. The interesting question is, does there exist an equilibrium where the informed voter stays home, right? If it's A, then S, or S, then B. So let's think about that. Let's say that you're voting for A if you know that it's A, and you're abstaining if you know that it's B. If I vote for A then, well, with probability alpha, we both voted for A, and that's great. One happiness point. Now, with probability 1 minus alpha, you didn't vote and I voted for the wrong person. 0 happiness points. So my expected utility for voting for A, when you're voting for A when A is best and staying out when B is best, is alpha. My expected utility for abstaining is, well, with probability alpha, you hit the nail on the head. You vote for A and A is best. With probability alpha, I get 1 happiness point. And with probability 1 minus alpha, we're just at a tie because neither of us voted. So that's a half of a happiness point. That works out to 1 plus alpha over 2. Finally, if I vote for B, when you're voting for A when A is best and staying out when B is best, well, with probability alpha, I just made a tie. So that's a half a happiness point. So alpha times 1/2. Plus with probability 1 minus alpha, I voted for B, B is best, you stayed out, I get 1 full happiness point for making the right candidate win. So that works out to 1 minus alpha over 2. You'll notice that if alpha is greater than or equal to 1/2, my best response is to abstain. And if alpha is less than or equal to 1/2, my best response is to vote for B. If alpha is less than or equal to 1/2, my best response is to vote for B. Now let's think about the world where I abstained. Do you want to deviate? Because right now you're voting for A when it's A and you're abstaining when it's B. If I abstained, then in the B world, you could have voted for B and we could get a full happiness point instead of the half for the tie. So you'd rather deviate there. So if alpha is greater than or equal to 1/2, then there is no equilibrium of this type. But if alpha is less than or equal to 1/2, now you're voting for A and generating a tie because I'm voting for B, which is not happening that often because alpha is less than or equal to 1/2. And then the rest of the time, I'm voting for B and generating a win. If you deviated to abstaining in the A world, you'd take us from 1/2 to 0. And if you deviated to B in the A world, you'd take us from 1/2 to 0. So you don't want to deviate. And if you deviated in the B world to voting for B, it would be the same outcome. And if you deviated in the B world to voting for A, you just make things worse. This is a Bayesian Nash equilibrium. If alpha is less than or equal to 1/2, then I vote for B, you vote for A when it's A, and you abstain when it's B, is a Bayesian Nash equilibrium. And you'll notice that it's worse for society than the one where I stayed out and you did the right thing. My expected utility for staying out when you were doing the right thing both times was 1, and my expected utility for voting B against you voting A and then abstaining is 1 minus alpha over 2, which is less than 1. I do worse when I vote. Even in the equilibrium where I vote, I do worse. And the reason for that is alpha percent of the time, I voted wrong and made a tie. Alpha percent of the time. There's waste alpha percent of the time. And notice that the A type of you, the type of you that knows that A is best for society, also does strictly worse. They get 1/2 of a happiness point instead of 1 happiness point for making A win. So the world where I vote is worse. Only the type of you that knows that B is best for society doesn't care. So it's Pareto dominated for me to stay out when both of you vote for the right candidate than it is for me to vote and for you to stay out sometimes. However, in this Bayesian Nash equilibrium, one type of you chooses not to vote. Now let's consider the situation where you abstain when it's A and you vote for B when it's B. So if I vote for A, when you're abstaining when it's A and you vote for B when it's B, then alpha percent of the time I get a full happiness point because I made A win and A is correct. And 1 minus alpha percent of the time, I made a tie. And that works out to 1 plus alpha over 2. If I abstain, well, with probability alpha, we both abstained. And so that's 1/2 of a happiness point. And with probability 1 minus alpha, you voted for B, and that's the right candidate. So 1 happiness point. So 1 minus alpha. So 1 minus alpha over 2 for that. 1 minus alpha over 2. And finally, the situation where I vote for B when you are abstaining when it's A and voting for B when it's B is, well, probability alpha, I screwed everything up and 0 happiness points. And with probability 1 minus alpha, we get the right outcome, 1 happiness point. So 1 minus alpha. You'll notice that if alpha is greater than or equal to 1/2, then my best response to you abstaining and then voting for B is to vote for A. And you'll notice also that neither type of you has an incentive to deviate from there. So in other words, if it's likely that A is the right candidate, then there's another Bayesian Nash equilibrium where I vote for A, you abstain when it's A, and you vote for B when it's B. This too is worse for all parties than the world where I abstained and you voted for the right candidate both times. So no matter what the alpha is, there are two pure strategy Bayesian Nash equilibria. If it's likely that we're in the A world, then I vote for A, you abstain when it's A, and you vote for B when it's B. And if it's likely that we're in the B world, the same works in reverse. I vote for B, you abstain when it's B, and you vote for A when it's A. And then there's the intuitive one, which is best for society. However, in every single pure strategy Bayesian Nash equilibrium of this game, one voter doesn't vote, or one type of a voter doesn't vote. There isn't an equilibrium where everybody votes. Moreover, the world where the informed voter votes is better for society than the world where the uninformed voter votes. In other words, the equilibrium where I stay out and you vote for the right candidate, Pareto dominates the equilibrium where I vote for the likely to be right candidate, you abstain when I'm right, and you vote for the right candidate when I'm wrong. There's a lot of waste. So in other words, the swing voters curse here demonstrates that the uninformed voter would rather stay home, but is capable of voting only in those situations where sort of the informed voter is lazy. That's pretty heavy, right? I hope that I breeze through this pretty fast. Make sure that you complete the analysis with me. Go back if you have to. But you'll notice that this stupid little two matrices has a lot of normative import because it suggests that maybe high turnout isn't as easy to generate as we think. And it also might introduce some perverse consequences. If nothing else, this suggests that there may be trade-offs that you hadn't thought about between how many people turn out to vote and the quality of the outcomes that they generate. I have no thoughts on this. I'm just food for thought. But I hope that you'll ruminate on it. You don't have too much time to ruminate right now, though, because over in the C block, we're going to turn things even more political by talking about what happens in legislatures. See you there. So here in the C block, I want to talk some pivotal politics again. I'm not going to waste too much time here. Imagine that we have a policy space. And imagine that we have the situation where there's a status quo that's on the left. There's a proposer whose ideal point is on the right. Just to keep life super simple, I'm going to normalize the status quo to 0. I'm going to say that the point at which the status quo is in this ideological space is 0. And that everything will therefore be with respect to that. All we'll be talking about is what's the gap away from 0. So the floor here is 0. Q is 0. P is something strictly greater than that. X hat P is something strictly greater than that. So the proposer's ideal point is to the right. The status quo is to the left at 0. And you'll remember in this private information example, what we have is two types of the voter that the proposer makes an offer to. Right? The proposer is choosing some policy in this space and is trying to figure out what offer they can get accepted that will be better than the status quo. Notice that they're far from the status quo. So they're making a proposal to a pivotal voter. The problem is that the pivotal voter comes in one of two types. There's a left type that's like over here, X hat V sub L. And this is the type of voter alpha percent of the time. With complementary probability, 1 minus alpha percent of the time, their ideal point is here at X hat V sub R. So there's a left version and a right version of the pivotal voter. The proposer is always here, the status quo is always here, but we don't know who we're making an offer to. If we're doing backward induction, then both types of the voter know what they're doing, and they will choose acceptance regions that go all the way over to Q, right? So they'll accept things as far to the left as Q. They won't go left of Q because that's not as good as Q. And they'll go as far over as 2x hat V sub them minus Q. So the left voter is willing to accept up through 2x hat V sub L minus Q. And the right voter is willing to accept up through 2x hat V R minus Q. Notice that the right voter will accept proposals further to the right than will the left voter. And I'm going to assume throughout that these voters will accept proposals that are on the furthest right point of their acceptance set. They accept when indifferent that way, so we don't have an unclimbable mountain. So this is where we left things last time. And my question is, what kind of offer should the proposer make? Because they don't know which offer to make, right? So in order to do that, let's plot the proposer's utility as a function of their offer, holding fixed what we just decided the two types of the voter will do. What I'm going to do is I'm going to plot this as a function of the proposer's offer. So we're going to say the proposer, aim it, Rob. So the proposer is going to offer some X, and we'll think about what their utility is for that X, expected utility, conditional on what we now have locked in that the two types of voter will do. I just want to mark a couple of key points along the way. I want to mark the 0 point. I want to mark Q equals 0. I want to mark Q. I want to mark 2x at VL. And I want to mark 2x at VR. If I draw lines through these 3 points, I've just carved the offers into 4 spaces. If I'm so far to the left that I'm left of the status quo, if I make an offer that's left of the status quo, that gets rejected by both types. Both types will reject that. And if I choose an X so far to the right that it's right of the right voter's acceptance point, then both types will reject. So at these two extremes, in these two worlds, way here at the edges, both types reject. Both types reject, and I'm stuck with the status quo. I'm the proposer now. I'm stuck with the status quo. If I make an offer too far to the left, it gets rejected by both types. If I make an offer too far to the right, it gets rejected by both types. These both lead to rejection. Notice that if I get rejected in these rejection regions, I get my utility for rejection, which is just the absolute value, which is the negative absolute value of x hat p minus q, which is 0, which is just negative x hat p, right? So my utility for getting rejected has nothing to do with x, so it's just gonna be a flat line. It's x hat p minus x hat p. That's my baseline utility, is minus x hat p. If I'm in the region between q and 2 x hat VL, if I'm between q and x hat VL, then what happens is at a q, I get accepted and I get that same minus x hat p. But then I get better and better. Remember, I get to get better and better in this region with a slope of 1. As I make offers that are still getting accepted, I get closer and closer to my ideal point. Both types are accepting in this region. Both types are accepting. And so I'm getting better and better at a slope of 1 until I get to 2x hat VL. And at 2x hat VL, we will assume that the left type accepts there. So there's a top of a mountain. There's a top of a mountain. If I choose a proposal at 2x hat VL, the left voter accepts, the right voter accepts, right? And so that's the best that I can offer in this region. The best I can offer in this region is 2x hat VL, which both types accept. My utility for that, if you work it out, is 2x hat VL minus p. That's my utility for making that offer and having it accepted, is 2x hat VL minus p. Now, what happens in this region? You might want to pause the video and tell me what happens in this region. In this region, which is to the right of 2x hat VL, but to the left of 2x hat VR. What happens in this region? What does the left voter do? What does the right voter do? Right, the left voter rejects here and the right voter accepts. Now comes the expected utility part. Now comes the alphas. This is going to be the power of alpha yet again. So, If I make an offer in this region, so let's just say that I chose an X over here. I'm just going to arbitrarily call it X. So what happens here is with probability alpha, you're the low type and you reject. With probability alpha, you're the left type and you reject here. And I wind up with the utility from the status quo. So it's alpha times minus P. And with probability 1 minus alpha, you are the right type who is accepting here. And so it's 1 minus alpha times X minus P. So alpha percent of the time you reject and I get my status quo utility. 1 minus alpha percent of the time you accept and I get my utility for that offer. If you work out what that is, then it works out to 1 minus alpha X minus P. 1 minus alpha times X minus P. Which means there's a line here still. There's still a line here, but it's not going up at the same rate. It's going up flatter than the initial line. Over here, it's going up with a slope of 1. And over here, it's going up with a slope of 1 minus alpha. It's going up with the slope of 1 minus alpha. Right? So if alpha is really high, so that it's very likely that you are the left type, then this goes up only very slowly. Because I'm not getting too many benefits from when you're the right type. Conversely, when alpha is really low, so that it's likely that you're the right type, who I like better, then this goes up a lot faster. As alpha approaches 1, it goes back to that slope of 1 sort of thing. Now I've got a mountain range because now I've got another top of the mountain. I've got another top of the mountain because remember, we're assuming, quote unquote, that the right type accepts at the top of this mountain. Otherwise, I have an unclimbable mountain. So if the right type is accepting here at 2x at VR, the top of that mountain, my utility for that, the altitude of the top of the second mountain is 2 times 1 minus alpha times x at VR minus P. I've got 2 mountains. I've got 2 mountains. I've got 2 mountains and I don't know which one is taller. And I need to find out which one is taller. Because whichever is the taller mountain, that's the offer that I'm going to make. You'll notice that I can get rid of almost all the offers. I'm only going to make one of 2 offers. I'm only going to make one of 2 offers. I'm either going to offer 2x at VL or I'm going to offer 2x at VR because those are the 2 tops of the respective mountains in my mountain range of utility. That's kind of heavy, right? So let's think this through. I know that the altitude of the top of the first mountain, that is simply 2x at VL minus P. That's just the utility that I get when I offer 2x at VL. And I know that the altitude of the second mountain, which I just got, was 2 times 1 minus alpha times x at VR minus P. So my question is, when is the second mountain taller than the first? When is the mountain on the right taller than the mountain on the left? You can work that out. Maybe you want to go work that out for yourself. So the right mountain is higher when 2 times 1 minus alpha times x at VR minus P is greater than or equal to 2x at VL minus P. We can get rid of the minus P's. Get rid of the minus P's on both sides. Now it's just 2 times 1 minus alpha times x at VR has got to be greater than or equal to 2x at VL. That's when the right mountain is taller. Divide both sides by 2. So now the right mountain is taller when 1 minus alpha times x at VR is greater than or equal to x at VL. The right mountain is taller when alpha is less than or equal to 1 minus x at VL divided by x at VR. So notice that first and foremost, alpha has to be sufficiently low. I make the right offer if I think it's unlikely that I'm up against the left person. If alpha is low, then I think you're to the right. And so I make the right offer. I make the offer that's at the top of the right, that gets me to the top of the right mountain, not the one that takes me to the top of the left. Why? Because I'm only going to benefit from making the left offer alpha percent of the time. And that's worse for me. I want to make the right offer. I want to make the offer that's on the right. But that means that alpha percent of the time, you're going to turn me down. So if alpha is less than or equal to 1 minus x at VL over x at VR. Now let's think about what happens as x at VL gets closer to x at VR. What happens if the 2 types of you aren't all that different? If the 2 types of you aren't all that different, then that ratio gets very close to 1, which means that the right-hand side of this inequality gets very close to 0, which means it's impossible to satisfy this condition. So I make the right offer in basically two situations. If I think that you are not very likely to be the left type, then I make the right offer. Or if the left type is really, really, really far from the right type, I make the right offer. Because it's not worth it to me. I don't want to make an offer that makes you happy if you're all the way over there. Otherwise, I make the left offer. So if alpha is greater than or equal to 1 minus x hat VL over x hat VR, then I just lock in the good outcome of offering 2x at VL so that I get to the top of that mountain, and really expected utilities had nothing to do with it because all that I did was placate the harder bargaining partner. I made the offer that made the harder bargaining partner happy. So notice that if alpha is high, if I think it's likely that you're a jerk, I make the offer that makes the jerk happy, and we never have gridlock. But I think that it's unlikely that you're the jerk, then I make the offer as if you're not a jerk. And then some of the time we have gridlock. We have gridlock alpha % of the time. So depending on how often I think that you're left or right and how far the two versions of you are apart from one another, those two factors, the likelihood that you're the left versus the right and how far left is relative to right, those two things determine whether or not I make an offer that makes the hard-ass version of you happy, or I make a probative offer knowing that the not-so-hard-ass version of you will accept it and the hard-ass version of you will reject it, and I just introduced waste because we're the status quo with probability alpha. Bargaining breakdown because of incomplete information. I accepted a little bit of risk of breakdown in order to get the reward of the right offer. There's a trade-off between how much risk I'm willing to eat and how much reward I get from making the better offer. It's a balance of how likely I think it is that you're left versus how far left is, which determines what the reward of my probative attempt to make the right offer. So in other words, this whole thing turns on two things. How likely do I think it is that you're one type of you or the other? And what does it mean to be one type of you versus the other? How far is the spread between your ideal points? And how likely is it that you're at one of those ideal points or the other? Those two things pin down the risk-reward trade-off, which can create waste because of inefficient bargaining outcomes, because sometimes I get a little bit too greedy, and I'm wrong. If I make an offer to you thinking that you're easy to work with and I'm wrong, then bargaining breaks down and we have legislative gridlock. Not because of nastiness, not because of ideology, but rather because I tried to be a little bit greedy and I couldn't quite get away with it. That's kind of a weird story when you think about it, but I think what's really cool is like choosing between the two offers. I think the two mountains and the range is the coolest part about all this. However, there's also this tragic outcome. We took a game that was easy for the legislators, and once we introduced a little bit of private information, we found that for any spread of ideology between the two types, there's an alpha that could make me create bargaining failure. And for every likelihood of you being the left or the right, for every alpha, there's a spread of ideal points that I could find that would also create bargaining breakdown. I can always find a set of games that has bargaining breakdown. I can pin them down. Kind of a sad outcome, but look at all the political intrigue. It turns out the political intrigue oftentimes creates waste. That's kind of what makes politics politics, if you ask me. But how heavy is that? All because of the power of alpha. So what do we talk about today? I mean, we ran the whole gamut and we ran it pretty fast. I'm really looking forward to working over the next few problem sets together because there's no way that one trip through this, plus your textbook, which you know is a thing and not just because of Lucky and Pozzo. Your textbook is a thing and you should work through it slowly if you need to. I just wanted to get you a little bit excited about this. It's a hard topic, but it's also a really exciting topic, right? Information is a fundamental aspect of our lives. Differences in information is fundamental, and it's interesting to wonder whether it creates problems. And I think from the C block, we saw that it can be a cause of problems because in bargaining situations where like there's a zero-summy flavor to our utilities. Given that, when I'm trying to do as well as I can without trying to push you too far, and if I don't quite know where your limit is, I might introduce risk that takes us back to the status quo. So we did see a source of waste because of information. And in there, we saw waste because of private information, because I couldn't figure out how to navigate the risk-reward trade-off just perfectly. But we also saw private information throw things up in the swing voters curse model, right? So there we had one enlightened voter who knew what was best for society and didn't cost them anything to vote. It's not like abstaining saved them some cost. And yet, we weren't able to find a unique equilibrium where the enlightened voter votes and the unenlightened voter doesn't. I mean, that's one equilibrium, but it's not the only one. In every equilibrium, we wind up with turnout that's low. We end up with a democracy that might not be fully representative. We end up with a large proportion of the population staying home, not because of costs. If you go back to the expected utility week, you'll remember that the PB minus C analysis said it's the cost of voting that keeps people from voting. What if it isn't? What if it's just the fact that they aren't quite the enlightened one? Or what if they're the enlightened one and they're staying home because the unenlightened ones are voting in one direction? In other words, information can throw things off for all sorts of reasons, and you'll see on the problem set there's a couple of others too. So whenever you see a political problem that seems like, oh, I don't know why this political problem is here. I don't know why there's gridlock. I don't know why there's war. I don't know why people don't vote. Anytime you see a problem, there's oftentimes a time-based argument with credibility and the future and all of that sort of stuff. And there's oftentimes an informational argument with types and beliefs and that sort of stuff. And then in the next couple of weeks, I'll show you how to fuse the two all the way when we talk about perfect Bayesian equilibrium. So we just talked about how to refine Nash equilibrium, how to extend Nash equilibrium to account for this type thing. And what we wound up doing in the A and B block is just smushing the games into one game, figuring out what the uninformed player would do, and then checking to see if the informed player thought that checked out. So we really just smushed the games. So Bayesian Nash equilibrium, this Bayesian analysis, is intimately related to Nash equilibrium, the simultaneous move games of complete information. And literally, we just turn one into the other to analyze it. That was the initial insight of the person that developed all this, John Harsanyi. You know, John Harsanyi was a really interesting figure. He had two PhDs. One was sort of in qualitative economics and one was in quantitative economics. And he was a high-minded, philosophically oriented person. He thought about being a priest for a while. And when he read political philosophy, it inspired him to come up with new mathematical models nobody had ever seen before. And he was able to analyze with this amazing nimbleness. He was just this super nimble, flexible brain who was just thirsty for new information from great thinkers and eager to try to encode them. And actually, when Harsanyi was working all this, when he was developing this Bayesian framework, he identified along the way a really interesting truism. And it's with that interesting truism in mind that I'd like to conclude with a provocative thought. If you think back to regular old mixed strategy Nash equilibrium of games of complete information, I think that's lecture 8. If you go back to lecture 8 with the P's and the Q's, you'll notice that there are games like matching pennies or the baseball game where there doesn't exist a pure strategy Nash equilibrium, right? So there's only equilibrium in mixed strategies. Nash's theorem doesn't promise anything in terms of pure strategy Nash equilibrium. It only makes a promise about a mixed strategy Nash equilibrium. So sometimes we wind up with games where there's no one certain outcome, where the outcome is bound to be somewhat stochastic, something random is happening. Now that's kind of weird because the game is only played one time, right? So in baseball, we animated this by saying, well, they don't throw the same pitch every time. But there isn't really a pitch. We're only playing the game one time. It's not like there's a sequence of pitches. It's a lot more like a penalty kick in soccer where you make one and only one kick. And the keeper makes one and only one decision about where to go in the goal. And when you think about it that way, it's hard to know what probabilities have to do with anything. You're not playing the game multiple times. You're only playing the game one time. It's a one-shot thing. And are we really supposed to think that you went and rolled a D20 so that you knew exactly the probability that you were supposed to go left or right? No, nobody does that. And so consequently, some people get worked up whenever they see a game that only has equilibrium and mixed strategies, or even just the interpretation of a mixed strategy Nash equilibrium. They say to themselves, well, this just isn't very realistic. Nash's theorem, it's great that it saved us from no equilibria, it's great that Nash's theorem gave us something to show the funding agency, but that's not enough. These equilibria don't seem realistic because in a one-shot game, players don't really randomize like that. That's a reasonable view. I mentioned it during mixing week. I mentioned it at the end of mixing week, and I wanted to revisit it here at the end of Bayesian week because it turns out that Harsanyi had a deep insight about the relationship of his own child, the Bayesian game, and the original game and game theory, the strategic form game, as studied by regular old vanilla Nash equilibrium. The name of this result, which is one of the coolest results names if you ask me, it's called the Harsanyi purification theorem. And so here's the idea. Imagine a game with complete information. Everybody knows that we're only playing one game. We're only playing baseball. We're only playing anti-coordination, matching pennies. We're only playing that game. Imagine we're only playing that game, complete information, one shot. No tree, no information sets. That game only has an equilibrium and mixed strategies, and so many people's hackles would be raised. It turns out that one game has a companion game where I'm one of two types and you're one of two types. Where there's like two-sided incomplete information like in the trade war from last week. And it turns out that I can choose that game just right. I can come up with the types just right and perturb the utilities in the game just right. It'll be very close to the baseball game, but it won't quite be all the way there. There'll be little bandwidths around the utilities. Sometimes I get a bump up from my utility and sometimes I get a bump down. But regardless, I can come up with clever little perturbations in these four states of the world that would happen if we drew it up that way, such that there's an equilibrium in pure strategies in the Bayesian game that generates the same outcome as the mixed strategy Nash equilibrium in the complete information game. So in other words, I can write down a game where we know each other's type perfectly. There's only one game, but the equilibrium is only in mixed strategies, so we don't know what the other will do. Or I can write down a game where we don't know one another's types, where I don't know what kind of you are, but I do know what each kind of you would do. You're playing a pure strategy. So in other words, every mixed strategy equilibrium in a complete information game can be purified to a pure strategy equilibrium in an accompanying close by perturbed Bayesian game. In other words, I haven't taught you about complete information models very much at all. I've only taught you about limiting cases of incomplete information models where the information finally converges to something where you would potentially know. But in the world where you really know the other player's type, there might only be a mixed strategy equilibrium, which doesn't quite make sense. All of the probabilities up to this point have actually been cousins of uncertainty about the other person's type. There's something really human about that, right? All the little tricks, all the little expected utility, all of those little best response correspondences that we worked through in the mixed strategy Nash equilibrium week, all of that was just a succinct representation of what I was trying to get to here. Bayesian Nash equilibrium in games where I don't quite know your type and you might not know mine either. And that's just a way more human story because it seems to me that you never quite get to know somebody else's type. You never quite get to know somebody else's preferences. You don't quite get to know what they know. That's an important part of the human experience. And that allows us to come up with pure, there's no uncertainty, certain equilibria, but where we're uncertain about one another. It seems to me that we're more uncertain about one another than we are about what each type of us does. And therefore, I kind of find today's lecture to be a really nice companion to the mixed strategy equilibrium lecture because it means that the more human thing can be used to justify the less human thing. Now, Harsanyi purification is actually just a bit of a parlor trick. It's not a very hard thing to pull off in most contexts. It's hard to show that it always happens, but it's not very hard. I'll put it on the problem set. It's not very hard to make it work. But it takes a deep insight. It takes something human. It takes reading political philosophy. It takes taking political science classes outside of game theory. It requires thinking hard about politics. It requires being observant. It requires just acknowledging something really deeply human about us, like we don't know one another's types. We don't know what kind of us we are. I don't know what kind of you are, and you definitely don't know what kind of me I am. That's just part of life. It's just a matter of combining the insights from looking around and reading hard books, and the creativity that you get to have once you know how to play in this particular sandbox. If you put those two things together, you can tell so many cool stories. You can tell cool stories about musical companions. You can tell cool stories about voters. Kind of sad. You can tell cool stories about bargaining in legislatures. But you can't tell them with just math. And you can't tell them really this way with just words. It seems to me that there's something really great about being able to see this tension, these truisms, these facts in our lives, the things that observant people notice. But it's easier even for unobservant people like me to notice them once we've encoded them, once we put them on the screen. You know, with our time together coming to an end, it's hard not to get a little bit philosophical about what it is I would like for you to have gotten out of this. And a big part of it is just appreciating what it is to see something that you thought you kind of knew enveloped in this particular apparatus. What does it mean for something so basic as I don't quite know what you want? What are the ramifications of that if we take that to its logical conclusions? I can't think of anything more satisfying than really getting something like that really right. In fact, I would rather get something simple, although still important, really right, than to get something complicated and potentially unimportant, not so right. I'd rather dig in one sandbox as far as I can go. And I think that we've been doing that lately, if you ask me. It seems that way, right? Basic, core, foundational, in the source code results about what it is to vote, what it is to bargain, what it is to try to make a friend and meet them at a show, and maybe they hate you. If you let yourself see all this as a language, if you see these as fables, then maybe all this struggle and maybe all the sweat you've been going through these last few really hard lectures, maybe they seem worth it, which is my hope. Regardless, we're about to make our final push up the mountain. We are getting to the crest, and it's going to be even a little bit steeper now. But if this hasn't gotten you excited, then I'm afraid I'm just not capable of it. Obviously, though, I have one last chance to get you fully inspired by giving you a fun, tricky problem set with all sorts of chances to reinforce this crazy, awesome learning that just happened. Geez, how many things just got put into your brain? And once you've worked through that problem set, I think that you might have a deeper sense about what exactly is going on. What's the mechanics of this? But I don't care if you really know all the mechanics. I care that you know, appreciate, and understand the punchlines. I also care that you know that sometimes there isn't a punchline to appreciate, but that doesn't mean that the analysis has to stop. If you internalize all that, then I'll be very proud to be your teacher. And it seems to me that many of you have. And so I've been feeling pretty proud of myself lately, not because of anything I do, but rather because of how awesome you are. Please keep it up. I'm looking forward to seeing you next week because your energy is something that I really thrive on as I try to push through these last few lectures. I really appreciate it. Thank you so much for that. Thank you so much for working so hard on these problem sets. And thank you so much for giving me some appreciation whenever you like one of these stupid lectures, which is pretty rare. So, all sappiness aside, we have some work to do. But in the meantime, thanks for watching.